Hi everyone, this is the first lecture of the second week. In this lecture, we're going to cover the ordinary least squares, or OLS. In this section, we'll cover the regression analysis to examine the relationship among quantitative variables. The technique used to predict the value of one variable, we call it dependent variable, or Y, based on the value of another variable, or independent variable, or X. To start, we focused on simple linear regression, which means we're using only one independent variable to explain the behavior of dependent variable. And the relationship between two variables is linear, not curved. Later, we'll relax these assumptions and use multiple regressions and nonlinear relationships. Here's an outline of what we're going to cover on week 2. We're going to talk about the population linear regression model, and we're going to move on to OLS estimator. On the second lecture, we'll cover the measures of fit, and we'll conclude with the least square assumptions. Here is a population regression model. In this case, we're looking at the simple linear regression model where we only have one independent variable. As we mentioned before, y is a dependent variable, x is an independent variable. Beta 0 is a y-intercept, beta 1 is a slope of the line, and ui is an error term. Since we're talking about the population regression model, beta 0 and beta 1 are unknown parameters. And we can estimate these unknown parameters by taking a sample from the data. So let's look at this example. Imagine that we are interested in the relationship between test scores and student-teacher ratio. And we only have 7 observations in this population. The population regression line fits a line that best fits the dots that we have. And the regression error is whatever the line cannot explain. So for instance, we fit this blue line, but this is the actual data point. So whatever is the difference between the actual observation and the regression line is an error term. Since we don't know the population regression models, we need to actually get the sample and estimate the sample regression model. So how do you estimate the best sample regression line? So say we have 4 observations for a sample. How do you draw a line that is best fit? One way is to minimize the sum of sample residuals or sample errors. So let's say we fit this line here and calculate the errors for each data point. The problem is that when you add up these errors, it can actually cancel out and end up with the 0 sum of sample errors. So when you add this error, which is negative, this error that's positive, it may end up canceling things out and it can give you a very small number. In this case, we can also fit another line this way. Here, this error would be negative, this error would be positive, and when you add these errors up, you may also get another small number. So the problem is that it's hard to minimize the sum of sample residuals because when you have positive and negative errors, they can end up canceling each other out and you may end up with a bunch of different lines that give you very small errors. One way to solve this problem is to minimize the sum of squared errors. So in this case, Instead of just minimizing the sum of errors, we square them, which makes every error positive. We call this ordinary least squares, or OLS. Let me give you an example of how OLS is actually calculated. So here we have the 4 data points from the sample before, and we also have 2 lines that fit the data points. So we have one line that is upward sloping, that is in black, and we have another line that is horizontal, that is in blue. First, let's calculate the sum of square differences for upward sloping line. So here we have a data point or first observation that has x value of 1 and y value of 2. And the error term will be the difference or this distance between this actual data point and the regression line. We know that the value of y on this regression line is 1 because this line is a 45-degree line. So we subtract the actual value or actual observation 2. We subtract 1, which is the regression line, from the actual value and square them to get the first term. The second error can be calculated by subtracting the regression line from the actual y value. So here the y value is 4. We know that the y value here is 2 because the x is 2 and it's at 45-degree line. So we subtract 2 from 4 and square it to get the second term. And we continue this to get the final value of 6.89. We calculate the sum of square error terms for the horizontal line by following the same strategy. So here we're trying to measure the difference between the actual data point and this horizontal line here. And again, we subtract 2.5, which is the horizontal line, from the actual value of 2 and square them to get the first term. Here we're trying to measure the distance between the horizontal line and observation here. So we subtract 2.5 from the actual value 4 and square it. And then if you do this for all 4 observations, then you get 3.99. Comparing 6.89 to 3.99, we can see that the horizontal line is a better fit because the sum of square differences is smaller. So the sample regression line can be written like this. Y hat I equal beta hat 0 plus beta hat 1 times xi. It looks a lot like the population regression line, except for some of the parameters have hats on them. The reason why we have these hats is because these are actually estimates. So we want to estimate yi and beta 0 and beta 1, which is from a population, but we don't really know the population beta 0 or population beta 1. So we need to take a sample and estimate them. And whenever you estimate something, you have hats. The reason why xi doesn't have a hat is because it's given in the data set. So in our case of trying to measure the relationship between test scores and class size, or student to teacher ratio, the student to teacher ratio is xi and it's given in the sample. So that's why it doesn't have hat. It's because it's not estimated, it's given. Equal to, same as population regression line, y hat I is called dependent variable, xi is called independent variable or regressor. Beta hat 0 is an intercept or the value of y when x is 0, also called a constant. Beta hat 1 is a slope, which is how much y changes for every unit change in x. Beta hat 1 is also called a regression coefficient. A lot of these have, for instance, yi or xi have i's because I indicates observation number. So in our question of looking at the school district, I would be a district. So when you have the first school district, it'll be x1. When you have an observation from the second school district, that'll be the x2. Sometimes we measure residual, which is calculated by subtracting the predicted value of y hat I from the actually observed yi. We showed this a couple of slides ago. We call this an error term. So basically we're trying to look at what is an error term or what is something that we cannot estimate. Oftentimes this residual is something that we forgot to include in the regression line. Something that explains yi that we forgot to include, or sometimes it could be a measurement error. Sometimes it's some measurement error that we couldn't have predicted. Let me get a little technical here and try to explain how the formulas for beta hat 0 and beta hat 1 are derived. Remember a few slides ago we said that OLS is a result of minimizing the sum of squared residuals. Here's a formula for sum of squared residuals. So basically error term or residual is the difference between the actual value and the predicted value. So actual is yi, which is what we observe, and the predicted is y hat I, which is what we predict from the regression line. And you square that and then you sum them up. So this is what we are trying to minimize. Because we're fitting the best line, we can substitute for y hat I our sample regression line, beta hat 0 plus beta hat 1 xi. And then once you substitute that, basically what you're doing is that you're minimizing this formula. When you take partial derivatives with respect to beta hat 1 and beta hat 0, that's how you get the formula for OLS. If you take partial derivatives with respect to beta hat 0 and beta hat 1, you get these formulas. And don't worry, you're not gonna be expected to calculate this by hand or memorize them. But it's always good to know where the formulas come from and how these estimators are derived. For some of you, you may recognize that the formula for beta hat 1 looks familiar. It is the correlation coefficient multiplied by standard deviation of y over standard deviation of x. Let's go back to our policy question of trying to understand the relationship between test scores and class size or student-teacher ratio. Basically, what we have is these sample data points represented by these dots over here. And what we're trying to do is we're trying to see if there's a relationship between these two variables, test scores and student-teacher ratio. In other words, we're trying to see what is the best fitted line. The problem of fitting a line to the scatter plot can be summarized by trying to estimate this population regression line, where the test score is what we are trying to predict, and student-to-teacher ratio is the independent variable. What we are interested in is beta 1, which gives you how much the test score changes when you change the student to teacher ratio by 1 unit. We're going to estimate the population beta 0 and beta 1 by typing in a simple command on Stata. The command that you want to type in Stata is regress the dependent variable y, in this case test score, and the independent variable x, in this case student-teacher ratio. Here in this command, we typed in comma robust, and you don't have to do this, and we'll discuss this further why sometimes you need to type this in later. When you type this command in, Stata will generate this output. It tells you a lot of information. First, it tells you the number of observations we have. So we have 420 observations, and very nicely, it gives you the coefficients. So this first number is the beta 1 estimate, and then the second number is a constant, or beta 0 hat. From the Stata output, we can tell that our sample regression line is test score is equal to the constant 698.9 minus 2.28 times STR. So what we're doing by typing in those commands in Stata is that we're fitting the best fit line that minimizes the sum of squared errors in the scatter plot that we have. So remember the complicated formula that we saw in terms of beta hat 0 and beta hat 1? The Stata is calculating that and generating those numbers. Let's look at the sample regression line more closely. So we had negative 2.28 as a regression coefficient. And what this means is that for district with 1 more students per teacher ratio on average, the test score is 2.28 points lower. One interesting thing about this constant is that if you take this literally, this is the number that you get when student-teacher ratio is equal to 0. So it means that for district that has 0 student to teacher, the average test score would be 698.9. But this doesn't make sense because there is no school district with 0 students. So even though the constant is some number here, it's not economically meaningful. Let's talk about prediction. Given some sample regression line, now we can predict what would be the predicted test scores given a particular student-to-teacher ratio. So let's say one of the districts in the data set is from Antelope, California, and that school district has a student-to-teacher ratio of 19.33. Given this number, we can actually have a predicted test score by plugging in 19.33 to our sample regression line. This gives you a value of 654.8, which is a predicted test score. But the actual test score of this district is 657.8. So the error term is a difference between the actual test score of this district, which is 657.8, and the calculated or predicted test score, which is 654.8. So the reason why there may be such an error term of 3 is because there could be some other factors other than student-to-teacher ratio that can impact the test score that we are not accounting for in our regression model.